Salam sejahtera, Doctor and Madam. My name is Fong Chuan Hui. I'm from 3BET 2/1, taking Bachelor of Electronic Engineering Technology in Telecommunication with honors. Now, it's great pleasure to be here, and I would like to deliver on the topic of design of sub-6 GHz microstrip patch antenna for 5G application using CST Microwave Studio. My supervisor is Wan Hazareda Bindi Wan Hassan. My course supervisor is Dr. Muhammad Inam Abisi. Let us start with introduction. Microstrip patch antenna are a category of flat antenna which has been developed in the half century. Microstrip patch antenna has become most popular and well known in the wireless communication system due to the benefit of low profile, cost to implement and fabrication. Sub-6 GHz and also called mid-band G is one of the frequency band and applied in 5G technology. Actually, there are two types of frequency in 5G, which are sub-6 GHz frequency band and millimeter wave spectrum band. Sub-6 GHz refer to mid and low frequency band. For low frequency band are under 1 GHz, while mid bands range from 3.4 GHz to 6 GHz. Lastly, radio frequency can be covered by sub-6 GHz. So what is the problem statement? Firstly is narrow bandwidth. Normally the bandwidth produced is around 500 MHz. Next is the low accurate and efficiency result, like unstable waveform. Lastly is the complicated design of antenna. The objective of the project is to design the microstrip patch antenna for 5G application. Second, to simulate the microstrip patch antenna using CST simulation software. To synthesize the simulation and measurement result in terms of dielectric properties, insulation loss, and electric field distribution. Literature review. There are some important literature review in my project. In the matter of first article, the design of the antenna in rectangular shape, the FR4 and PLC used as substrate. It advantages good result in impedance matching, simple design, but it produces unwanted noise on the antenna. In the matter of second article, the loom elements are used. FR4 used as substrate material. They are light in weight, high efficiency, wide bandwidth, but the antenna is complicated design. In the matter of third article, a circular patch on the substrate, FR4 used as substrate material. The antenna is stable far field result and stable gain, but the antenna design is complex. In the matter of fourth article, combination of microstrip antenna and Yagi antenna. The substrate material is FR4. The antenna produces high gain, low cost, larger bandwidth, but the antenna is complicated design, has a low volume in resonant frequency. Let us move on the next part, methodology. In methodology, I apply flowchart to determine the process. Firstly, process start with the design and simulate the antenna using CST software. Then, if the simulation result is good, can continue to the next part, to the next process. If not, you need to go back the first step. After that, proceed with the fabrication in the industry. From here, you need to do the comparison of the simulation result and hardware result. If both the results are approximately matched, then it can be applied in the application. If not, you need to go back to the first step, design and simulate the antenna. Software that used to design antenna is CST Studio Suite. What is the material for designing the patch substrate, and ground. The Lodger 3003 is used as the substrate material. The copper is used as for the patch and the ground plate. Before design the antenna, there are some calculations need to proceed in order to get this important parameter. This is the formula. This is the formula for the width of patch. After that, we also need to calculate the length of the patch. The microstrip feet wave, the microstrip feet width also need to calculate by this formula. This leads us to the next section, is design of antenna. So this is the S-shape of the antenna that I designed on CST simulation software. The first diagram is show the front view of the proposed antenna. The second diagram is the back view of the proposed antenna, which means is the ground plate, In the ground plate, I use the partial ground plate in order to improve the bandwidth of the antenna. S parameter describe the input-output relationship between ports. As you can see from the S parameter, it shows the frequency at 3.4924 GHz with around negative 33.85 dB. Then we apply negative 10 dB to determine the bandwidth. The first point is 3.03 GHz and the second point is 4.58 GHz. We take the higher values, 4.58 GHz minus 3.03 GHz is equal to 1.5 GHz. So this is a result of VSWR. VSWR is a function of reflection coefficient which describes the power reflected from the antenna. So when someone says that the antenna is poorly matched, very often it means that the VSWR value exists too for a frequency interest. So we can say that the smaller the VSMR is, the better the antenna is matched to the transmission line and the more power is delivered to antenna. The purpose of VSWR response that shown in this figure as is used to verify the frequency response further. Hence, the bandwidth of the proposed antenna can be determined under value 2. Finally, for the conclusion, in the end, a sub-6 GHz S-shaped patch antenna can work in 5G application. The method has provided good way to achieve the result. So this is the reference that helped me to complete the project. So this is a Gantt chart for PSM1 and this is a Gantt chart for PSM2. So that's all for my presentation. Thank you. Now I will show the demonstration of my project. This is an S-shaped antenna that I designed on CST simulation software. For the component, the substrate material that I use is Lodger 3003. The dielectric constant is 3. For the width of the substrate, which is 30 mm, and the length of substrate is 35 mm. It same goes through the ground plate. For the ground and the patch, I use the copper material to design it. Actually, for the original patch shape is the rectangular shape, but I want to modify it to become the S shape, so I cut here and here equally to become the S shape. For the width of the patch is the 30 mm and the the length of the patch is the 12 mm. So this is the microstrip fixed line. For the length of the fixed line is 20.5 mm and the width of the fixed line is 1.2 mm. So this is the ground plate of the proposed antenna. For the ground plate, I use the partial ground plate to design it in order to improve the bandwidth of the proposed antenna. So let us do the result. So this is the result of S parameter. As you can see from the S parameter, we can get the frequency at 3.4899 GHz, which is nearly close to the 3.5 GHz. So we use the negative 10 dB to determine the bandwidth. For the first point is 3.03 GHz and the second point is 4.58 GHz. In order to find the bandwidth, we need to take the higher value to minus the lowest value. 4.58 minus 3.03 equal to 1.55 GHz. Next to the VSWR result. Voltage standing wave ratio. VSWR is a function of the reflection coefficient which describes the power reflected from the antenna. So this purpose of VSWR is used to verify the frequency response further. From here, we can see that the frequency is located at 3.4899 GHz. And if you want to find the bandwidth, we can use the value of 2 to find the bandwidth. The VSWR, the value is 1.04004. The smaller the VSWR value, the better the antenna is matched to the transmission line and the more power is delivered to the antenna. That's all for me. Thank you.